Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 18, 2025, about 5 days ago. This paper introduces InfCam, a depth-free, camera-controlled video-to-video framework that uses infinite homography warping to lock in camera rotation cleanly, then learns the remaining parallax end-to-end for high post-fidelity and strong synthetic-to-real generalization. The paper is titled, Infinite Homography as Robust Conditioning for Camera-Controlled Video Generation. And as we'll see later, the combination of rotation-only conditioning and aggressive trajectory augmentation really changes what reliable camera control looks like. Also, the authors shared an InfCam GitHub repo that is pretty practical. You will find the inference and training code, helper scripts to download the WAN 2.1 backbone, and sample data to run quick demos. The README walks through environment setup, checkpoint downloads, and running preset camera trajectories, or your own videos. Figure 1 makes the promise concrete because it shows InfCam following a user-specified camera move while keeping the scene coherent. This figure shows 3 example trajectories on the left, where the origin is pinned to the first frame in red. The right side pairs each source video strip with the generated strip so you can compare how the viewpoint shifts. The bottom row also changes focal length, and the dashed box marks the original field of view. Figure 2 explains why infinite homography conditioning gives steadier camera control than depth reprojection. Infinite homography warping means the method applies only the camera rotation, which stays clean in 2 dimensions, and then learns the leftover translation parallax from data. The top row shows a source frame, the H-infinity warped frame, and a clean generated result. The bottom row contrasts depth reprojection, where depth errors create broken conditioning that leads to artifacts. Figure 3 turns that geometric idea into an actual training recipe that keeps camera control clean. The full diagram lays out a DIT block, meaning a diffusion transformer block, where most attention layers stay frozen, but a homography-guided self-attention layer is trained so it can use the H-infinity warped latent as a stable rotation cue. The left side shows source and target videos going through a 3-dimensional variational autoencoder into latents, which are then noised. The right panel shows the warping module, where H-infinity warping handles rotation first and camera embeddings carry translation information. Table 2 shows that the method delivers better real-world camera control and better-looking videos at the same time. Rotation error and translation error measure how closely the generated video follows the target camera motion, and lower values mean tighter post-fidelity. The bottom row has the strongest numbers, with rotation error about 3.16 and translation error about 0.44. The same row also posts the best FID and FVD scores, which means cleaner frames and smoother videos overall, even without ground truth target views. Table 1 shows that the method stays closest to ground truth on a controlled synthetic benchmark, even when the focal length changes. This table summarizes August MC versus results using PSNR and SSIM for pixel and structure similarity, and LPIPS for perceptual distance where lower is better. In the shared intrinsics block, the highlighted row reaches APSNR of about 22.7. In the different intrinsics block, the same row stays strong at about 22.3, which supports robustness to camera intrinsic shifts. Table 3 shows which ingredients actually cause the post-fidelity jump, because it turns the method into a step-by-step ablation. Ablation means you remove one component at a time to see what it contributes. The left columns toggle trajectory augmentation, intrinsic augmentation, and the warp module. The right side splits results into shared intrinsics versus different intrinsics, and the best row is the full setup, which reaches APSNR of about 24.4. Alright, the big takeaway is that InfCam gets reliable camera control without depth by locking in rotation through infinite homography warping and learning the remaining parallax end-to-end. The second takeaway is that strong trajectory and intrinsic augmentation helps the model generalize beyond narrow training camera moves. That combination points to more practical, post-production style viewpoint editing for video diffusion models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.